Welcome to lecture 11. In this lecture, we are going to talk about two methods, the variation of parameters and the method of undetermined coefficients. These two methods are used to calculate particular integral for a differential equation which is non-homogeneous and with constant coefficients. Okay. First, the method of variation of parameters. Okay. So this method is used to find particular integral of second order differential equations. Okay. So method of variation of parameters is we can use it if we are dealing with second order differential equations, and we can use it to find the particular integral of second order differential equations. So to see how to use this method to find particular integral, let us first consider the second order differential equation with constant coefficients, which is given by this equation: the second derivative of y with x square plus k1 times first derivative of y with x plus k2y is equal to capital X, where capital X is a function of x only, or it may be a constant. K1 and k2 are constants, so it's a second order because the second derivative is the highest derivative, first degree, non-homogeneous because of right hand side, differential equation, ordinary with constant coefficients. Now we know how to calculate the complementary function of this differential equation. Okay, so for that you can write the characteristic equation, find roots. There will be two roots, either two real or equal, or a complex pair. So based on that you can write the complementary function. Okay, so let the complementary function be this, and complementary function is the solution of homogeneous system. So let the corresponding homogeneous system has a solution y is equal to c1 y1 plus c2 y2. Okay, so there will be two roots of characteristic equation. So based on two roots we can write the solution in this form, where y1 and y2 are two independent solutions. Okay, because y1 and y2 are two independent solutions, then the Wronskian of y1 y2 will be non-zero. Okay, so the Wronskian w of y1 y2 is non-zero and is given by, okay, so we know what is Wronskian. It is the determinant of y1 y2, and in the second row the derivative of y1 and derivative of y2. So if we calculate this determinant, which is y1 y2 dash minus y2 times y1 dash, this determinant must be non-zero because y1 and y2 are two independent solutions. And so the particular integral by method of variation of parameters can be calculated by this formula, which says that particular integral is equal to minus y1 integral of y2 x over Wronskian dx plus y2 times integral y1 x over Wronskian dx. Okay, so and y1 and y2 are known because they are calculated in the complementary function, and capital X is already known, it is the right hand side function, and Wronskian we can calculate as determinant of y1 y2 y1 dash y2 dash. So then we can solve these two integrals, and that will give us the particular integral. Okay, and once we know the particular integral, then we can write the complete or general solution as complementary function plus particular integral. Okay, so this method is the method of variation of parameters to solve second order differential equations, and this method is sometimes difficult to apply because of the integrals, which may be a bit lengthy to solve. Okay, so you can use this method particularly when you are asked to find the solution of differential equation by this method. Okay, so say for example, say using the method of variation of parameters solve this differential equation. So it's a second order differential equation which is non-homogeneous because of right hand side and with constant coefficients. First we can find the characteristic equation, roots and complementary function. Characteristic equation is m square plus 4 equal to 0, so there will be two roots. M is equal to plus minus 2i, which is a complex pair, so we can write the complementary function as c1 cos 2x plus c2 sin 2x. Okay, the real part of this complex is 0, so e raised to power 0x is 1. And cos 2x and sin 2x, they are two independent solutions of this, so we can uh, uh, write that y1 is cos 2x and y2 is sin 2x, so we can calculate the Wronskian w, okay, as determinant of y1, y2, y1 dash, y2 dash. Okay, so y1 is cos 2x, one of the solutions, and y2 is sin 2x, the second solution here. And then because y1 y2 is known, cos 2x sin 2x, so that's first row. And in the second row we have the derivative of these two, so cos 2x derivative is minus 2 sin 2x and sin 2x derivative is 2 cos 2x. And then determinant of this, so it will be the cos 2x into 2 cos 2x minus sin 2x into minus 2 sin 2x, so 2 cos square 2x plus 2 sin square 2x, so it will be 2 because cos square plus sin square is 1. And once we know y1 y2 Wronskian and capital X is already there, tan of 2x, then we can find the particular integral by using this formula. Okay, so we can substitute y1 cos 2x, y2 sin 2x, capital X is tan 2x, Wronskian is 2. Similarly in the second integral we can substitute the values, and then we can solve the integrals. Okay, so tan 2x is sin 2x by cos 2x, so second integral is simply integration of sin 2x, and in the first integral it is sin 2x by cos 2x, so we have sin square 2x over cos 2x, and sin square can be written as 1 minus cos square, so again we can just rearrange. Okay, so it is 1 minus cos square by cos, which can be written as secant minus cos 2x, and this integral of sine 2x, so we can integrate and find a solution of this. Okay, and once we know the particular integral, we already know complementary function, then complete solution is this complementary function plus this particular integral. Okay, so we can write the complete solution of the differential equation. Okay, say I take another example. Say use the method of variation of parameters, solve this second order differential equation, non-homogeneous, constant coefficients. Okay, so again first write the characteristic equation, which is m square minus 2 times m plus 1 is equal to 0. Okay, so homogeneous equation is to be solved for finding the complementary function. So characteristic equation is this: it has two roots, both real and equal, 1 and 1. So complementary function is c1 e power x plus c2 x times e power x. Okay, so c1 e power x, c2 x times e power x. Now this is y1 e power x and y2 is x e power x. Both are independent solutions, so we can calculate the Wronskian, which will be a non-zero value. Okay, so Wronskian W is again y1 is e power x, y2 is x e power x, and in the second row derivative, so exponential derivative is exponential, so it remains same, and x e power x, so we apply for derivative product rule, so x times exponential derivative is same, plus exponential times x derivative, which is also plus e power x. And now we can solve this determinant. Okay, so you can easily see that it is e power 2x. Once we know Wronskian y1 y2 and capital X is e power x log x, right hand side, so the particular integral, we know the formula for method of variation of parameters, and particular integral is this minus y1 y2 integral of y2 x over w plus y2 integral of y1 x by w. So we can substitute all these values here. Okay, so it will be minus e power x, this will be x e power x into e power x log x by Wronskian, which is e power 2x. Okay, so we can substitute all this. E power 2x will cancel out inside the integral. Similarly inside the integral here e power 2x will cancel out, so we can easily rewrite this. and then we can integrate this integral of x log x. Okay, so log x first function and x second function we can integrate by parts. Similarly, integral of log x, so log x first function and 1 as second function we can use integration by parts. Okay, so this will be the integral value. Okay, so finally we can just combine them to write the particular integral value as this. So the complete solution will be complementary function plus particular integral. Okay, complementary function plus particular. Okay, so it is quite simple, but sometimes the numerical may be such that the calculation becomes so much lengthy that we usually avoid this method. Okay, the second method is the method of undetermined coefficients, and for this method, say let there be a differential equation of nth order which is non-homogeneous and with constant coefficient. So nth order, so this is the highest derivative is nth, and k1 k2 kn they are all constants. Right hand side makes it non-homogeneous. Okay, and now the method is method of undetermined coefficients. Okay, so first this method is also used to find the particular integral. So and complete solution is complementary function plus particular integral. That means complementary function, again we have to find you using the usual rule that we write the uh, characteristic equation, find its roots, and then write the complementary function. Okay, so the first step is that you calculate the complementary function by finding the roots of characteristic equation, and this is already discussed in the previous lectures now. So to find the particular integral using method of undetermined coefficient, what we do is we use trial solution containing unknown constants. Okay, and then we substitute that trial solution in the original differential equation to find the constants. Okay, and then the particular integral it becomes known. So okay, the trial solution is substituted in the original differential equation and the unknown constants are calculated. Okay, and finally we write the complete solution as complementary function plus particular integral. Okay, so now the only question is that how to write this trial solution. Okay, how do we know that what trial solution we can use. Okay, so we cannot solve every differential equation by this method. Okay, we can only solve um, the differential equation when this right hand side capital X is a function such that its derivatives are either terminating or repeating. Okay, so if this right hand side function, if its derivatives, okay, the derivative of x, second derivative of x, third derivative of x, if we calculate all the derivatives, the derivatives are either terminating, that means after some time the derivative becomes zero. Okay, or repeating. Okay, the same derivatives are coming again and again. For example, the polynomials. Okay, because say you have right hand side x square. Okay, so then x square derivative will be 2x, then it will be 2 and then 0, and then all derivatives further will be 0, so derivatives are terminating. Or the right hand side is a trigonometric sine or cosine function. Okay, say it is a sine x. Okay, so then sine x derivative is cos x, again derivative minus sine x, then minus cos x, then plus sine x. So uh, if we keep derivative, that derivative starts repeating. Okay, the same functions will come again and again. So or similarly the exponential, say you have e power x as the right hand side, then e power x derivative is e power x, again e power x derivative is e power x. Okay, so same function is repeating. Okay, so only for such functions where derivative of capital X is either terminating or repeating, then we can use this method of undetermined coefficients, and then we can use trial solutions for those functions. Okay, and so for example, say if our right hand side capital X is say tangent of x. Okay, then we cannot use this method because derivative of tan x is secant square x, then derivative of secant square x will be 2 secant x into secant x tan x, then further its derivative will be more complicated, and then again next derivative will be further, so they are neither repeating nor terminating. Okay, so we cannot use this method for such functions. Now if you are given right hand side capital X with a function such that it is a polynomial or trigonometric sine cos or exponential or combination where it is terminating or repeating, then how to write the trial solution? Now we talk about this. Okay, so the trial solution are written based on capital X and also depends on the complementary function. Okay, and how to write, say capital X is a given a exponential function. Capital X right hand side is e power ax, and it also depends on the complementary function. That means this capital X is e power ax and e power ax is not in the complementary function. Then trial solution we can write as c1 e power ax. Okay, constant time e power ax. Okay, so if you have the right hand side capital X as a exponential function, then we write in the trial solution a exponential function multiplied by a constant, provided that this exponential function is not present in the complementary function. Okay, if exponential function is present in the complementary function, okay, then the trial solution is written in this form: the constant time x times e power ax. Okay, so exponential function is multiplied with the x, provided that this function also is not in the complementary function. If this x time e power ax is also in the complementary function, then we multiply with another x and write in the trial solution as x square e power ax multiplied with some constant. Okay, provided that this is also not in the complementary function, and so on. That means if this is also in the trial complementary function, then we multiply with another x and we can take constant time x cube e power ax. Okay, so a trial function for exponential function is easy to write. Okay, it is the same exponential function if it is not in the complementary function. If it is there, then x times, provided x time exponential is not in the complementary function, and so on. Okay, second possibility is that the right hand side capital X is a sine or cosine function. Okay, so say I take the example of sine function. Similar is true for cosine. Okay, so a capital X is a sine ax function. Then in the trial solution we take both sine and cos. Okay, the reason is very simple, that the derivative of sine ax is cos ax. Okay, and then derivative of cos ax is sine ax. Okay, derivative of sine ax is cos ax. Okay, plus minus sign goes in the constants. Okay, so not to worry about plus minus sign. So basically the, if I keep on derivating sine ax, then it will be either sine function or cosine function. So in the trial solution we take both sine and cos. Okay, provided that both, either sine or cos, either of them is not in the complementary function. Okay, not in the complementary function. If either sine or cos in the are present in the complementary function, then we apply similar rule, we multiply with an x. Okay, so if in case sine x or cos x is in the complementary function, then trial solution is constant time x sine x plus constant time x cos x, provided that x sine x or x cos x are not in the complementary function. Okay, if they are also in the complementary function, then we multiply with another x. We write x square sine x plus x square cos x. Okay, so in sine or cos we take both sine and cos because their derivative contain a repeating factor of these. Okay, in exponential we take only exponential, because if you keep on differentiating this first derivative, second derivative, third derivative, will get only one thing, which is the trial solution, this exponential. Okay, but in the derivative of sine we get sine as well as cos. Okay, third possibility is that we have a polynomial type term, capital X is x power m, then the trial solution will be this. Okay, x power m itself and all its derivatives. Okay, so x power m derivative will be m minus 1. Okay, so then x square x constant, and then rest are 0. Okay, so it will be a polynomial with all the terms constant, linear, quadratic, and so on up to x power n. Okay, with different constants. Okay, and these are not only the function. There is say one more function I can define is say capital X is exponential time cosine function. Okay, similar exponential times sine function can also be there. So the trial solution for this is e power ax and c1 cos bx plus c2 sin bx. Why we are getting this trial solution is, if you differentiate this x, okay, then derivative by product rule will be uh, e power ax minus b sin bx plus a e power ax cos bx. Okay, so what we get is e power ax sin bx term and e power ax cos b term. If you take another derivative of that, again you will get only those combinations. So if you take say second, third, fourth, fifth derivative of that, so only these two combination of terms will they are repeating. Okay, so these two combination of terms will come with some constant value. Okay, so the trial solution is easy to write for this. Okay, so basically if you are given any capital X on the right hand side, and if you have to apply method of undetermined coefficient, you try and calculate what derivatives are there. If it is terminating or repeating, you can write the trial solution. If it is non-terminating and non-repeating, then you cannot write the trial solution for this method. Okay, say for example use the method of undetermined coefficients to solve this differential equation. Okay, so it's a second order differential equation, non-homogeneous with constant coefficients. First we'll find the complementary function, and for that we write the characteristic equation, which is m square plus 2 times m plus 4 is equal to 0. Okay, so and then this we can solve to find two roots. So roots are minus 1 plus minus root 3i, complex pair, so we can write the complementary function as c1 e power minus x into c1 cos root 3x plus c2 sine root 3x. Okay, so this is the complementary function e power ax, a is minus 1, into c1 cos bx, b is root 3 plus c2 sine bx, b is root 3. Okay, so once we have this, and we have to use method of undetermined coefficients. So we see what is capital X. Capital X is this 2x square plus 3 e power minus x. Okay, and both these function x square and e power minus x, they are not in the complementary function. If you compare e power minus x, e power minus x is here, but this e power minus x is a multiplied with cos function, or e power minus x is multiplied with sine function. There is no single e power minus x. Okay, so both these are not present in the complementary function. That's one thing. Okay, so trial solution we can write for x square polynomial there will be three terms: constant, linear x, and x square. And for exponential there will be one term, which is this exponential. Okay, so trial solution we can choose as this: y is equal to ax square plus bx plus c. Okay, so this polynomial because of this 2x square, and d e minus x because of this exponential. Okay, so we have to take here arbitrary constants a, b, c, and d. Okay, so now we can substitute this y back here in this differential equation, and we can calculate what is a, b, c, and d. And once we know a, b, c, and d, we can substitute them here, and that will be the particular integral. Okay, so to substitute this here, we need the first derivative of y and second derivative of y. So we can calculate the first derivative of y. Okay, so y derivative will be 2ax plus b, and derivative of exponential is exponential with negative sign. So 2x plus b minus d e power minus x. And for second derivative, we will differentiate this one time. So it is 2a, derivative of b is 0, and plus de minus x. So 2a plus de minus x. Okay, so now we can substitute all these three on the left hand side. Okay, right hand side remains as it is, and then we can compare and calculate a, b, c, and d. Okay, so substituting these terms in the original differential equation, so differential equation becomes this is the second derivative term plus 2 times first derivative plus 4 times y. Okay, so this is left hand side, and right hand side is 2x square plus 3e minus x. Okay, now we can combine constant terms, linear terms, quadratic terms, exponential terms on the left hand side. Okay, so constant terms, the linear term, quadratic, and exponential terms. Exponential is de minus x minus 2 de minus x and plus 4 de minus x. So we can combine them. Okay, And then what we have to do is we have to compare both sides. Okay, so if we equate the coefficients of same terms, so exponential coefficient is here is 3 and here it is 3d, so that means 3d equals 3. Okay, similarly coefficient of x square is 2 and coefficient of x square is 4a, so 4a equals 2. Coefficient of x is 4a plus 4b, and on this side coefficient of x is not there, so that means coefficient of x must be 0. So 4a plus 4b equals 0, and this constant term here, and there is no constant term here, so this constant term must be 0. So 2a plus 2b plus 4c must be 0. Okay, so we equate on both sides the coefficient of different polynomial terms and exponential function, and immediately we can calculate d as 1, a as half, and if we put a as half we can calculate b, and then a and b we can substitute here to calculate c. Okay, so immediately you can calculate a half b minus half c 0 d1. Okay, and then we can substitute all these values back here in the trial solution, so we will have y, which is the particular integral. Okay, so we can write the particular integral as ax square, which is half x square, minus half x, so that's plus bx, c is 0, and plus d e power minus x, d is 1. Okay, so complementary function is there, particular integral is there, we can write the complete solution as usual as complementary function plus particular integral. Okay, so the method is very simple. Okay, say I take one more example here, solve this differential equation using method of undetermined coefficients. First find the characteristic equation, which is m square minus 1 equal to 0, so 2 roots m is equal to plus 1 minus 1. Complementary function, because the roots are real and distinct, so it is c1 e power x plus c2 e power minus x. Okay, trial solution. Now here capital X is exponential into cos, and this function is not in the complementary function. Okay, so we can write the trial solution as y is equal to exponential e power 2x into a cos 3x plus b sine 3x. Okay, so whenever you have exponential into cos, it is exponential into cos plus exponential into sine. Okay, so this, and then we can substitute this on the left hand side, equate and find a and b constants. Okay, so first derivative and second derivative required. Okay, we got to put second derivative here, so we calculate two derivatives. First derivative is calculated and then second derivative is calculated, so you can try this, that these are the derivatives, and then substitute the second derivative and y value on here on the left hand side. Okay, so once we substitute, you can combine the terms of e power 2x cos 3x and e power 2x sine 3x. Okay, and then you can compare both sides. Okay, so we combine e power 2x cos 3x terms, there are two terms. Okay, similarly e power 2x sine 3x, e power 2x sine 3x, and on the right hand side is, so e power 2x cos 3x, it has a coefficient of 1 on right hand side, and e power 2x cos 3x, it has a coefficient of this minus 6a plus 12b, so that means minus 6a plus 12b will be equal to 1, and e power 2x sine 3x has a coefficient minus 6b minus 12a, which is not here, so minus 6b minus 12b must be equal to 0. Okay, and then so these two equations we can solve and calculate a and b. Okay, so a is minus 1 by 30 and b is 1 by 15, and then we can substitute them back here to find the particular integral. So y or the particular integral is e power 2x a, which is minus 1 by 30 cos 3x, plus b, which is 1 by 15 sine 3x, and then the complete solution is the complementary function plus this particular integral. Okay, so this method, okay, of undetermined coefficients. In the next lecture we'll talk about simultaneous linear differential equations, where we'll solve a system of differential equations, okay, which are ordinary differential equations, but then the dependent variables are more than one now. Okay, have a very good time.